What is up, everybody? Mr. Kozad back with another video lesson. Today's topic is a calculus lesson, and today we're going to talk about volume by slices. Section 5.2 for most calculus textbooks, and this is part one. This is going to be a two-part video series. So part one, you're going to have to come back for part two, okay? So I hope you're ready to have some fun with this. This is a really exciting lesson. I love this lesson a lot. But before we go on, do anything else, I got to tell you, today's a great day to be alive. I hope you're doing well wherever you are, however you found this video. Welcome. I'm happy that you're here, and I really hope that the next 15 to 20 minutes we spend together is valuable and helpful for you. If you like what you see here, be sure to leave me a comment and let me know. If you want something to be different or want a topic to be covered that I haven't covered yet, please let me know as well. So here we go. Let's jump right in. So there are some key concepts that we need to actually, I'm going to add a page. Let's do a blank page before this one. So there's a couple notes that I want to write down before we actually get into our problems. Okay. First of all, volume. Okay. We have to remember what volume is. Okay. So volume is always three-dimensional. Okay. So let's write some of these things down. Volume is three-dimensional, meaning we have three different directions that we can measure. Depth, length, width, or length, width, height. There's a lot of ways that we can talk about that, but volume is going to be in three dimensions. So you obviously remember like three-dimensional figures where you draw like a cube like this or something along those lines. So we're going to be finding the volumes of these areas, but what's going to be interesting for us is we're going to be using some curves to define the base. Which we'll talk about in a minute. Okay, so thing number one is that volume is three-dimensional. Thing number two that you're going to have to remember for this lesson is we actually can take the integral of area, and when we take the integral of area, that's going to equal volume. That might not make a ton of sense right now, but it will as we go through these problems. Okay, and another thing that you're going to see in today's lesson that I want to point out to you is we are going to talk about area formulas, and we're going to format it like this: A of x. And when you see that, what that's going to be is that's going to be the area of a cross section. You're like, Kozad, what in the world are you talking about? Okay, this all is going to make sense as we start going through some problems. But these are kind of three key concepts for you to remember before we even start about this lesson. Okay, so now we can jump right into the actual first problem. So example one, here's what it's going to look like. It says find the volume with the indicated base and slices. Okay, now what I need everybody to do, okay, I need everybody to write this down if you're taking notes. If you did not print these notes and you're writing them down, write this down really quickly and then put your pencil down. And it's really important that you watch me draw this figure, what's happening here, because I'm going to have to do some things that are kind of interesting. Okay. All right. Step number one when I draw this shape, okay, is I'm going to draw my x-axis, or I'm sorry, my y-axis and my x-axis. And you might be asking, well, Kozad, why did you draw them like that? Okay, because it's defining for me the interval from 0 to 3, so that's quadrant 1 only. Okay, so then what I'm going to do is I'm going to draw the curve y equals x squared on the interval 0 to 3. So x squared, this easy function, it's quadratic, so it's going to look something like this. Okay, now I start at 0, like you see here, and I end at 3. So I'm going to label that right here. Okay, now this is where I need everybody to pay attention. Okay, so what I'm going to do, I actually need to rotate this picture. Okay, I need to rotate this picture a little bit. So I'm going to show you what's going to happen. So I'm going to rotate this just a little bit. I'm going to make it a little bit smaller. Okay, and I'm going to zoom that in like this. Okay, so what we're actually doing here is this shape that you see here is going to be the bottom of our three-dimensional figure. Okay, it's the bottom. And what we're going to do is we're going to build shapes up off the screen that would imagine this literally laying flat on your paper and then building a set of squares that's going to come up off of your paper. Squares, because we have square slices, it's going to come off of your paper. Okay, and we're going to stack several of these squares right next to each other. Now, it's impossible for me to draw all of these squares, but I'm just going to draw a few of them and try to illustrate for you what's happening. Okay? So the length of a square, we know a square, we've learned this since you were in pre-K. Square is a four-sided shape where all four sides are the same. Okay, so imagine building a square that comes up off of the page that has varying lengths, side lengths. So you can maybe start to see that as I build this, as I slide to the right, as I get closer to 3, those squares get larger and larger and larger. So imagine infinitely many of those squares that are stacked right next to each other. You're going to create a three-dimensional solid. Okay, you're going to create a three-dimensional solid. So what we can actually do with that, okay, or what we do next, is the next thing we want to do is we want to find the area of a cross section. Now a cross section is if I took one of these shapes, if I sliced it in half down the middle, okay, one of these shapes would be a square, okay? So the cross section here are squares, and you have to remember how to find the area of a square. So the area of a square is the side squared, okay? Where, here's what we need to talk about too. What does S equal? Where S in this problem equals x squared. S is going to equal x squared. Now again, this is where people get really, really tripped up, okay? Look at this big square that I drew, the last one that I drew right here. This is the side, okay? That's the side length. Well, how do we figure out what that side length equals, okay? It's not 3. 3 is the x value. So I take 3 and I actually plug 3 into the function x squared. So 3 squared gives me 9. So the side length of this square is actually 9. And you should probably agree, like as I slide from 3 towards 0, the side lengths are going to always be getting smaller. Every time I go closer to 0, the side length's getting smaller and smaller and smaller. Okay? So again, to find the length of the side, you're going to use the function x squared. So if I go back to my area equation, area equals s squared, but I know that the side is going to, I use the function x squared. So that's x squared squared. So my area is actually going to be x to the 4th. Okay, now here's what we're going to do next. One of the 3 things I had you write down earlier was that the integral of area is going to equal the volume. So what we're going to do is we're going to take the integral of the area, and our area function is x to the 4th, and we're going to integrate that on the interval that they give us from 0 to 3 with respect to x. And this is actually a pretty easy integral to find. The integral of x to the 4th is 1/5 x to the 5th, and we're going to evaluate that from 0 to 3. So again, super easy integral to evaluate. This is a definite integral, so we plug the 3 in for x. So 3 to the 5th is 243. Over 5 is just 243 fifths. When I plug a 0 in for x, I just get 0. So my answer here is going to be 243 over 5. Volume is always cubed, so units cubed. So this number represents the volume of the shape that you would get if you took this base, this x squared, this base here, and built consecutively larger squares starting at 0, going all the way to x equals 3, bigger and bigger and bigger and bigger squares that you stacked right next to each other. The volume of the shape that you'd get is 243 over pi. I'm sorry, over 5. Okay? I think that understanding the picture is the hardest part. So we'll try again on the next one. Okay? Just stick with me. If you're confused, stick with me a couple more problems, and then we'll see how we're feeling. Okay? All right, here's example 2. Same directions. Find the indicated base, or the volume with the indicated bases and slices. We're changing, this problem now goes to semicircular slices. Okay, so step 1 is to draw a graph of this function. Okay, So this function is y equals x on the interval 0 to 2. Okay, y equals x is a straight line. Starts at 0, ends at 2. So I'm going to label that. Got my x-axis and my y-axis. So again, what I'm going to do here is I'm going to rotate this because it's easier for me to see in 3 dimensions if I rotate it just a little bit. Okay? And again, what we're going to do here is we're going to build semicircles right next to each other to create a 3-dimensional shape. So I'm going to try this one as well. So I'm going to go through each one of these sections. These cross sections is going to be a semicircle that, remember, is going to come up off the screen. So each semicircle that I draw gets consecutively bigger. And I think that this shape is actually a little bit easier to see the 3-dimensional solids start to take shape. You can imagine building these semicircles right next to each other. They get larger and larger and larger until you get to 2. Okay? Now, when I do a, oh, I guess I accidentally rotated that too. Okay? So when I get to this, let's look at just this last circle to help us understand. Okay? So the area of a circle, we all should remember, is pi r squared. But remember, I don't have a full circle, I have a half circle. So it's going to be 1/2 pi r squared. Where r equals, we got to figure out what r equals. Okay, so r, remember, is half of the diameter. Well, the diameter here is going to be found by just taking the function, whatever the function was defined, as x. So we want to take half of that value. So r, in this case, is going to equal 1/2 of the x value. So think about this last circle, for example. If the x value is 2, plug that in the function, and y equals 2 as well. So if this distance here is a total of 2, cut that in half, and on this particular circle you get the radius equals 1. Now every other circle is going to have a radius smaller than 1. It's going to get all the way down to you have a radius of 0 when you have x equals 0. But you're always going to be able to find that radius by taking half of the x value. Okay, so let's actually plug that into our function. So we have a of x equals 1/2 pi times 1/2 x squared. Okay, so let's do a little algebra there to clean that up. So we get 1/2 pi times 1/4 x squared. And then I'm going to go ahead and take the 1/4 and the 1/2 and get 1/8 pi x squared as my area. Okay. All right, next. So now we're going to integrate this. So we're going to take the integral from 0 to 2. That interval was defined for us, of the area, which is 1/8 pi x squared with respect to x. Again, this is not a complicated integral to find. 1/8 pi is all a constant, so we can slide that out. The integral of x squared is 1/3 x cubed, and we're evaluating this from 0 to 2. So now all we have to do is we have to plug in our upper bound and our lower bound and figure out what we've got. So when I plug in 2 for x, 2 cubed is 8. 8 times 1/3 is 8/3. 8/3 times 1/8 is going to be 8/24 pi, which ends up being 1/3 pi as my volume. Forgot units cubed, you should put that. Okay, 1/3 pi units cubed. Okay, so there's one more problem that we're going to do together, and same directions that you've seen. Find the volume with the indicated base and slices, but this time we're changing to isosceles triangle slices. So isosceles triangle slices. And you might be a good idea to remember that isosceles, the definition, it has 2 equal sides. So in this particular case, the base is going to equal the height. Okay, the base is going to equal the height. So we've got a function square root of x. So let's start by drawing that graph. Okay. So square root of x looks something like this. Again, it's going to go from 0 to 4. And let's label our x-axis and our y-axis. Okay, again, I'm going to rotate this because it's a little bit easier to see. And you're thinking, well, Cosette, I can't rotate my paper. Okay, I can't rotate it after I draw it on my paper. You don't have to. Okay, this is just for me to kind of visually try to show you in the best way that I can what's actually happening here. So our cross sections are going to be isosceles triangles. So I always start by just drawing a few cross sections here. Again, it's impossible to draw all of them. Okay. Now, you're going to draw a isosceles triangle and make the dashed line the base. So as I'm drawing these triangles, you can start to maybe see what the shape looks like as we create it as a solid. So they progressively get larger and larger and larger. And remember, guys, it's impossible for me to draw all of them, but there's going to be infinitely many of these connected to each other here. So let's talk about area. Okay, so the area of our cross sections, our cross section is isosceles slices. So that's the area formula for a triangle. Okay, now we need to figure out what the base is. Okay, well, if you look at the last triangle that we drew, the base is going to be this distance here. Okay, so the base here, it's not 4, okay? I need to plug 4 into the function, okay? So the square root of 4 would be 2. So the base in this last rectangle, or isosceles triangle, would be 2. So here, the base is going to equal the square root of x. Whatever your x value is, take the square root of it, and that's how you're going to get your base. Remember, we're using the function that's defined for us, okay? So more specifically, I know that the base and the height are the same, so that is going to end up being 1/2 times the square root of x times the square root of x. Again, for an isosceles triangle, the base and the height are the same length. So that ends up being 1/2 x. Square root of x times square root of x gives me x. So now I'm ready to take my integral. So my integral from 0 to 4, that was defined for us in the problem, of 1/2 x dx. Again, super easy integral to evaluate. We have 1/2 times 1/2 x squared, evaluated from 0 to 4. And now we just plug and chug, so we take that upper bound and plug it in. 4 squared is 16. 16 times 1/2 is 8. 8 times 1/2 is 4. So we get 4 units cubed. Again, we don't have to subtract the lower bound because when I plug in 0 for x, I get 0. So 4 minus 0 is just 4. So 4 units cubed would be the volume of the three-dimensional figure that's created using isosceles triangle slices consecutively right next to each other, going from 0 all the way up here to 2. I'm sorry, to 4. Lots of material in that, guys. It's lots. So I know that you might need to rewatch that a couple times. Again, I think the hardest part is visualizing what's actually happening here. You can actually Google volume slices and do an image search, and there's some projects that people have done to kind of illustrate this with some pretty cool pictures that you can find. Once you see the picture and what's actually happening, I think this gets a lot easier. So I hope this was helpful for you. Please let me know if you need additional help or additional direction, and then be looking for part 2 of volume by slices. See you guys.